Today we are going to discuss the reactions of alcohols where basic properties of alcohols are involved. We will discuss the reaction of alcohols with hydrogen halide. We will also discuss Lucas test and Victor-Meyer test, which are used to distinguish between primary, secondary and tertiary alcohols. We will discuss the mechanism of reaction of hydrogen halide with alcohol. We will also discuss the reaction of phosphorus halides and thionyl chloride with alcohol with their mechanism. We will then discuss the oxidation, the dehydrogenation and dehydration reactions of alcohols. Reactions of alcohol which involve basic properties of alcohols. We will discuss now. Alcohols actually undergo nucleophilic substitution reaction via replacement of hydroxy group. The hydroxy group is not a very good leaving group, and that is why the reaction of alcohol is performed in acid, so that a protonated alcohol is formed, which is also called oxonium ion. The oxonium ion now has the good leaving group water, which is less basic as compared to the hydroxide ion which is present in alcohol. The reaction of alcohol with hydrogen halide takes place according to this reaction, in which alcohol react with hydrogen halide to form alkyl halide and water. The order of reactivity of alkyl halide follows the order like hydroiodic acid is most reactive towards alcohol, then is hydrogen bromide and then is hydrogen chloride. Similarly, the tertiary alcohols are most reactive towards this reaction, then are secondary alcohol and then are primary alcohol. We will see later on when we will discuss the mechanism that rearrangements are possible in secondary and tertiary alcohols, but are not possible in most primary alcohols. Alcohols react with HI, HCl and HBr as we have discussed in the earlier slide. Here HI is reacting with primary alcohol to form ethyl iodide, but if we are using HBr, the reaction conditions are a bit drastic, that is we are using sulfuric acid, and if we start with HCl, which is least reactive towards alcohol, then we see that we have to use zinc chloride as a catalyst to undergo this reaction. We are now discussing a few more reactions in which sodium bromide is reacting with butanol, or hydrogen chloride is reacting with tertiary butanol, or HI is reacting with ethyl alcohol. In all the cases you can see that when we are using tertiary alcohol, then reaction can take place at room temperature. When we are using HI, which is highly reactive, then also the reaction is very easy. Now we will discuss some tests by which we can distinguish between primary, secondary and tertiary alcohol. Say for example, we have 3 containers, but we do not know which container has which acid, whether it is a primary alcohol or a secondary alcohol or a tertiary alcohol. Then a test called Lucas test is assigned to distinguish between them. Lucas reagent basically comprise of zinc chloride and hydrochloric acid. Alcohols when react with zinc chloride and HCl, they form chloroalkanes. These chloroalkanes are insoluble in alcohol, whereas the alcohols are soluble there. The reason or the test basically is based on this property of alcohols and chloroalkanes. Alcohols are soluble, whereas chloroalkanes are insoluble. Now, when chloroalkane are formed by the reaction of Lucas reagent, a cloudiness appears in the solution and we are able to identify whether the alcohol is a primary alcohol or a secondary alcohol or a tertiary alcohol. The order of reactivity of alcohols is that tertiary alcohols are most reactive, then are secondary alcohol and then are primary alcohol. So, since tertiary alcohols are most reactive, they will react fastest with Lucas reagent and they will form cloudiness almost immediately, whereas secondary alcohols are slightly less reactive. So, they will react, they will take about 5 minutes time. So, cloudiness appears after 5 minutes, whereas in case of primary alcohols, since they are very slow in reaction, cloudiness does not appear at all at room temperature. Cloudiness may appear on prolonged heating. So, a test is utilized for the distinguishing of primary, secondary and tertiary alcohol. Now, here we have another example of allyl alcohol. You can see here this allyl alcohol is seems to be a primary alcohol, but it has a double bond next to the alcoholic group. That is why the molecule is highly stabilized, and when the Lucas reagent reacts with it, almost immediately allyl chloride is formed, but allyl chloride is not insoluble, and that is why allyl alcohol cannot be distinguished by Lucas test, although it reacts with Lucas reagent immediately. Victor-Meyer test. This is another test for distinguishing primary, secondary and tertiary alcohols. This test involves 3 steps. In step 1, hydroiodic acid reacts with alcohol to form iodoalkanes. In the second step, silver nitrate is added to the same solution. Iodoalkanes react with silver nitrite and form alkyl nitrites. In the third step, nitrous acid is added into the solution. Primary alcohols form nitrolic acid, which give red color with potassium hydroxide. Secondary alcohol form pseudonitrile, which gives blue color in potassium hydroxide, whereas tertiary alcohol do not react at all with nitrous acid. So, we can distinguish the primary, secondary and tertiary alcohols by this method. We will now discuss the mechanism of the reaction of hydrogen halide, in particular hydrogen chloride with zinc in presence of zinc chloride. Now, zinc chloride basically is a Lewis acid and it forms a complex with alcohol. Here the lone pair of electron on oxygen actually are donated to electron deficient zinc. As a result, this complex is formed, followed by the addition of chloride into it to form alkyl halide or alkyl chloride. Now, the question arises, why tertiary alcohols are more reactive? The reaction of alcohols with Lucas test basically involves carbocation. Carbocation formation in case of tertiary alcohol results in the formation of a tertiary carbocation, whereas in case of secondary and primary alcohol they generate secondary carbocation and primary carbocation. Now, since you know that secondary and primary carbocations are less stable than tertiary carbocation, tertiary alcohol show higher reactivity towards alcohol, and that is why you can see here the order of reactivity of alcohol is tertiary alcohols most reactive, then is secondary and then is the primary alcohol. We can elaborate more upon the mechanism in this way, that methyl alcohol and most primary alcohols react with hydrogen halide via SN2 mechanism, whereas secondary and tertiary alcohols react with hydrogen halides via SN1 mechanism. In both the mechanism SN1 and SN2, the first step is the protonation, that is acid reacts with alcohol to form oxonium ion. Now, the mechanism of reaction of primary alcohol with hydrogen halide. As we have earlier discussed, first step is the protonation. The alcohol forms protonated alcohol, followed by the attack of halide ion from the opposite side. As a result, there is formation of alkyl halide or haloalkane. This kind of mechanism is called SN2 mechanism, in which the base attacks from the back side and the leaving group, hydroxy group, is leaves the substrate. As a result, alkyl halide is formed. Now, the mechanism of reaction of secondary and tertiary alcohol with hydrogen halide follows SN1, where first step is the protonation step, that is alcohol reacts with hydrogen halide, forms protonated alcohol. The second step is the removal of leaving group water and formation of carbocation. The third step is the attack of the nucleophile halide ion to form haloalkane. The nucleophilic substitution, as we have discussed, follows SN1 or SN2 mechanism. In case of SN2, the rate of the reaction is decided by the concentration of both protonated alcohol as well as the halide ion, whereas in case of SN1, it is only the concentration of protonated alcohol which decides the rate of reaction. So, in other words, we can say that acid protonates the hydroxy group of alcohol, converts it into a better leaving group and increases the concentration of oxonium ion. Now, more the oxonium ion, higher will be the rate of reaction. We will now discuss some reactions in which nucleophilic substitution takes place, but in the meantime or during the mechanism rearrangement also takes place. We will take the example of 3-methyl-2-butanol. This 3-methyl-2-butanol, when reacts with hydrobromic acid, it forms 3-methyl-3-bromobutane. The hydroxy group is present at position 2 here, but when you see the product, you see that the bromo group has not gone to the position where hydroxy group was earlier placed. Now, what has happened during the reaction? We will discuss here. See, first step is the protonation. The hydroxy group gets protonated, followed by the removal of water molecule and formation of carbocation. Look at this carbocation, this is secondary in nature, and when one of the hydrogen from this next carbon with its pair of electron migrates to this electron deficient carbon, then what happens is that there is formation of a tertiary carbocation, and this tertiary carbocation being more stable is converted from a secondary carbocation. Now, when attack of bromide takes place, the resultant compound is 2-methyl-2-bromobutane. In these two examples, one of them is neopentyl alcohol. See, neopentyl alcohol is a primary alcohol. Even then, the product you are getting here in case after the reaction with HCl is not conforming with the simple replacement of hydroxy group with the chlorine atom, whereas 1,2-methyl shift actually takes place. In the next example also of 3,3-dimethyl-2-butanol, you can see that there is a migration of methyl group in the product. You can see that the product formed is 2,3-dimethyl-2-chlorobutane and not 3,3-dimethyl-2-chlorobutane. We will now discuss the reaction of primary alcohol with hydrogen halide, and here you will see that no rearrangement takes place. When this normal pentanol reacts with sodium bromide in presence of H plus ion, bromopentane results. There is no rearrangement taking place in this kind of reaction. So, this shows that primary alcohol undergo SN2 type of mechanism or follows under the SN2 type of mechanism, whereas secondary and tertiary alcohols follow SN1 type of mechanism in which carbocation is formed. We will now discuss the reaction of alcohols with phosphorus halides and thionyl chloride. When it reacts with alcohol, it forms haloalkane. The beauty of this reaction or the difference from the earlier reaction which we have discussed is that there is no possible rearrangement in this case, whereas in the earlier case we have seen that rearrangement was possible with secondary and tertiary alcohol. Similarly, here you can see that alcohols follow this order of reaction, that is methanol reacts fastest with phosphorus halide and thionyl chloride, and then is primary alcohol, and then is the secondary alcohol. Here we are taking an example of neopentyl alcohol. When this reacts with phosphorus tribromides, it forms neopentyl bromide, or which is also called 2,2-dimethyl-1-bromopropane. In the earlier slides you have seen that when neopentyl alcohol reacted with hydrogen chloride, there was rearrangement in the product which is not seen when we reacted upon this neopentyl alcohol with phosphorus tribromide. We will now discuss the reaction of alcohols with phosphorus pentachloride or and thionyl chloride. Primary and secondary alcohols react to form chloroalkanes without any rearrangement. The PCl5 when reacts with alcohol forms haloalkane along with POCl3 and HCl, whereas thionyl chloride forms sulfur dioxide and HCl. The reaction of alcohol with thionyl chloride is a better method for the conversion of alcohols to alkyl halides, reason being that two byproducts formed here are gases and they leave the reaction mixture easily without any additional cost added to the reaction. Reaction of alcohol with phosphorus tribromides follows SN2 mechanism. In this kind of reaction, first of all, phosphorus tribromide is attacked by the lone pair of electrons and it forms a complex with the removal of bromide ion. Now, this bromide ion attacks the electron deficient carbon from the back side, resulting in the formation of bromoalkane, which is formed by the inversion of configuration. Actually, if we start with an alcohol which is optically active and we undergo reaction with phosphorus tribromide, the product bromoalkane formed will have inversion of configuration. Say for example, we start with a dextrorotatory compound, dextrorotatory alcohol, the product formed will be a levorotatory bromoalkane. In case the reaction of alcohols takes place with thionyl chloride, then the mechanism followed is SNI, that means substitution nucleophilic internal or intramolecular. In this case, see what happens is that this alcohol react with thionyl chloride, there is removal of HCl and formation of this complex, and then since the chlorine is present within the molecule, this attacks the electron deficient carbon from inside. That is why there is retention of configuration, or in other words we can say that if we start with an optically active dextrorotatory alcohol, the product formed will be a levorotatory haloalkane. Next we will discuss the oxidation of alcohols. Primary alcohols are oxidized to carboxylic acids when they are treated with strong oxidizing agents like alkaline KMnO4 or concentrated nitric acid. When oxidation is done on propanol, the product is propanoic acid. When the oxidation is done on butanol, normal butanol, the product is the butanoic acid. Secondary and tertiary alcohols, on the contrary, when oxidized they give different products. Secondary alcohols form ketones, whereas the tertiary alcohols they give carboxylic acid with less number of carbon atoms as compared to the starting alcohol. Or in other words we can say that secondary alcohols give carboxylic acid which have less number of carbon atom than the starting alcohol. Similarly, tertiary alcohol also form carboxylic acid which have less number of carbon atom than the starting alcohol. It is only the primary alcohol which give carboxylic acid with similar number of carbon atoms. Alcohols undergo selective oxidation also. See what is selective oxidation? That is, alcohol react to form react with oxidizing agent converted into aldehyde. Since aldehydes are also highly reactive, they further oxidize to carboxylic acid. If we stop the oxidation process at aldehydic stage, we require some specialized reagent, and this process is called selective oxidation of primary alcohols. The reagent utilized here is PCC, also known as pyridinium chlorochromate. This pyridinium chlorochromate when reacts with primary alcohol stops the oxidation at aldehydic stage. In case of oxidation of secondary alcohol, secondary alcohols are oxidized to ketones. The oxidizing agents used are sodium dichromate in acidic medium or chromic acid in acidic medium in presence of acetone. This mixture is also called Jones reagent. When we undergo oxidation of 2-butanol or in presence of appropriate oxidizing agent, it is converted into ketone 2-butanone. This is cyclohexanol. When it is oxidized, then it forms cyclohexanone. We will now discuss dehydrogenation of alcohol. Dehydrogenation means removal of hydrogen from the molecule of alcohol. When hydrogen is removed from the molecule of alcohol, the resultant product is aldehyde or ketone. When this primary alcohol is treated with copper at high temperature, the resultant is the product is the propanol or an aldehyde. When secondary alcohol undergoes the same reaction, there is formation of ketone, whereas when it is tertiary alcohol which is treated with copper at high temperature, then the product is neither an aldehyde or a ketone, but an alkene. Actually, in case of tertiary alcohol, removal of a water molecule takes place from the alcohol molecule. We will now discuss the dehydration of alcohol. Dehydration means removal of water molecule from the molecule of alcohol. When water molecule is removed from alcohol, alkenes are formed. Depending upon the nature of alcohol, like if it is a tertiary alcohol, the reaction will be fastest, with secondary after that, and with primary alcohol the reaction is slow. This can be seen in the reaction conditions we have shown here. This normal propanol being a primary alcohol requires sulfuric acid at 170 degrees centigrade. 2-butanol, a secondary alcohol, requires sulfuric acid at 100 degrees centigrade, and 2-methyl-2-butanol, which is a tertiary alcohol, requires sulfuric acid only at 70 degrees centigrade to undergo this dehydration process. In today's lecture, we have so far discussed the reactions of alcohols where they show basic properties. We have discussed the reaction of alcohol with hydrogen halides. We have discussed the test like Lucas test or Victor-Meyer test to distinguish between primary, secondary and tertiary alcohols. We have also discussed the mechanism of reaction of hydrogen halide with different classes of alcohols. We have seen that rearrangement occurs in case of secondary and tertiary alcohol, but it does not occur in case of primary alcohols. We have also discussed the reaction of phosphorus tribromide, phosphorus pentachloride and thionyl chloride with alcohol. We have also discussed the substitution nucleophilic internal which involves thionyl chloride. We have discussed the oxidation of primary, secondary and tertiary alcohol, also the dehydrogenation and dehydration of alcohols under different conditions. In the next lecture, we will discuss the reactions, the formation and the properties of dihydric alcohol. We will also discuss what actually are dihydric alcohols, how they are formed and how they are useful in day-to-day life. Thank you.